morning again. We'll continue with this casual, general discussion, general relativity if you like. We're still in special relativity though. We're still on what's going to be known as flat space, and we'll move to curved eventually. Okay, so flat space, the space-time interval in x, y and z are Cartesian coordinates. It doesn't have to be Cartesians, it can be polars, r squared, theta squared, and so on. Now let's move on to a little bit infinitesimally close to the x coordinate, and another step a little bit infinitesimally close in the y direction, and similarly in the z, a differential, t plus delta t, z plus delta z, x goes to x plus dx, right? So we define a differential space-time interval like this. The difference between this and this point and this space-time point is simply this. Okay, so close to, infinitesimally close to x, y, z, c, t, we have the space-time interval that looks like this. So we define three classes of these space-time intervals. First one where dt equals 0, and therefore ds squared is dx squared plus dy squared plus dz squared. Actually, I'm going to call this dx squared, because it can be in any of the x, y, z directions. So take the square root. Alright? The square root is going to be positive or negative, and we'll get a real space-time interval. We'll call this a space-like interval. Now we'll say that there is no movement in space, only movement along time. Time is going forward, but we're stopped in space. ds squared equals negative c squared dt squared. And so therefore then when we take the square root, this interval is seen to be imaginary. We'll call this one a like-like space-time interval. So real intervals are space-like and like-like are imaginary. Okay? Finally, set ds squared itself equal to 0. The space-time interval is now 0, and we can say that dx squared plus dy squared plus dz squared is c squared dt squared. So therefore then, this big dx squared equals c squared dt squared, dx equals c dt, and objects travel at the speed of light. So that's a straight line through the origin, and in x, y, z space defines a cone. Okay, so the forward cone in time, there can be a backward cone in time, but for the forward cone in time, that's where we live. Actually, we live in here. You can communicate with objects or events in here, but you cannot communicate with events here. We'll also assume that time goes forward and that we cannot communicate for now, we cannot communicate with events back here. One way or another, when ds squared equals 0, we're following a null path in space-time, and objects travel at the speed of light. Now, a Lorentz transformation is a device for keeping this guy invariant under s squared goes to s dash squared. So we'll talk about that later. I just want to talk generally now about, we were talking about the equivalence principle. I'm leading up to the differential space-time element. We'll clean the board of this, we don't need this just yet. Now, in one of the previous talks, I noticed that I rotated something without rotating the unit vectors as well. In the new coordinate system, the unit vectors also have to be rotated. They're still unit vectors, but when you take the dot product to find the magnitude, that dot that, the unit vectors are still unit vectors, so I dot I will still give you 1, and it's still the same result. But I made a mistake. I often make mistakes. I'm not thinking properly. I think better when I have an audience. I've only got a camera, but I know there's an audience behind the camera, but for me, I'm used to the classroom. And also, students are very good at picking up on mistakes. We want to transit from flat space-time to curved space-time. The language of that transformation is actually tensor calculus, I'm going to try and bypass it. Well, we'll see. I'll talk about it generally first. The general idea is this. Flat space. Parallel lines never meet. The sum of the angles inside a triangle adds up to 180 degrees. Flat space. However, let's look at this room. Concrete was poured down here one time. Concrete is then allowed to settle. The question is this floor flat? Now think about it for a while. Okay, a better one for you guys since you're elsewhere. You're sitting beside a totally undisturbed, no ripples swimming pool, full of water. The water is dead calm, and you ask yourself the question, is that swimming pool completely flat? You have to think about it. Well, the answer is that locally it appears flat. Locally, where you're sitting, on the small scale, it looks flat. However, if you projected that swimming pool all the way across to London, you would notice its curvature, yeah? If your swimming pool was the Atlantic Ocean, you'd definitely notice its curvature. The same is true for the floor here. Locally, we're flat. This is only an approximation to the large scale. The large scale geometry of the Earth is curved. All right? Vasco da Gama figured that one out. Who was it? Magellan, sorry. Magellan also noticed the Magellanic Clouds because he went around the world and he went down south. This flat space-time interval is going to be generalized to a curved one, but just let's look at the geometry first and see how it fits in with the falling elevators. Okay, so flat space, here it is. However, that's only a local patch on the curved Earth, which on the large scale has a radius r and is curved. So let's look at our patch and put it somewhere else. Make it look curved. Now the sum of the angles of a triangle on the surface of the Earth is always going to be greater than 180 degrees, slightly greater. But locally, we can approximate them, with the flat space. So generalizing from flat to curved space is what geometry wants to do, even if there's no physics in it. And that was done by George Bernard Riemann, who lived between 1836 and 1866 and died young, I guess. So we talk about local flatness and global curvature. Local flatness will turn out to be inertial, and global curvature will turn out to be, as interpreted by general relativity, it may not be the real theory of the world, global curvature will be non-inertial. This non-inertial space-time is referred to usually as Riemannian space. And this one here is Minkowski. After Minkowski from 1864 to 1909, and I think that he was Einstein's teacher. Okay. So, how do we define the shape of space? We define the shape of space by saying, what does light do there? Light travels on null geodesics. Light, anything traveling at the speed of light, objects or photons of light travel on null geodesics where ds squared equals 0. And the x squared is c squared dt squared. And the speeds, objects travel at the speed of light. Now, okay, so let's take the elevator now, and we'll take the guy out of it, and we make the elevator continue to travel at a constant speed. Well, let's make it speed 0 first. Relative to an outside observer. Somebody's watching. This person is watching and is stationary with respect to this frame of reference. Okay? So, stationary with respect to this frame of reference, when V equals 0, now I shine a beam of light from here to here. The beam of light goes straight across. I could shine it at an angle, but I'm choosing to shine the beam of light always parallel to the x-axis. So now, parallel to the x-axis, the beam of light goes straight across and is parallel to the x-axis. Now, when V is equal to constant, depending on what the V is, the light starts off at the same spot. But this guy has moved up after a certain amount of time, and after another amount of time, and another amount of time, and another amount of time, keeps moving up at a constant rate. I'm going to exaggerate that a little bit. So in the time Vt, this light beam will just move down, towards the floor. And what is the t? Well, since we're at it, here's what the t is. Let's say the width of this elevator is L. H is just Vt over L. We're not really worried about that. We're just saying that it goes down by a certain amount. Now we have another elevator over here. Okay. Now this is traveling vertically also. But we'll give it an acceleration. Okay. So if we have this guy at an acceleration, here's what happens. We shine the beam of light. The same observer is watching. This one's going vertically up at a constant rate, but this one is accelerating upwards. What does the beam of light do? Well, we know the way accelerated objects fall, right? When you want to graph an object falling through a height h, it's parabolic in shape. Okay, so let's see, how far down will the beam have gone? This height here, if there's a constant acceleration a, is going to be given by h. Okay, we'll say v can be 0. So this height, the amount of distance that the beam has fallen, is a half a t squared, and its path is curved. Now this corresponds exactly to what we want in terms of geometry. The curved path corresponds to non-inertial. Frame of reference, FOR, okay? This is inertial. It's a straight line. Both are inertial. But of course, if everything is referred to this observer who's in this stationary frame, stationary with respect to the XY frame. So that's a recipe for where we're headed. Curved paths are going to be what we need to define what happens to objects in non-inertial frames of reference. And it's obvious, it's not rocket science. You don't have to be thinking general relativity for this. No general relativity here at all yet. I'm going to write down a simple transformation. Now instead of writing frame of reference all the time, I just write for. In future, that's what a frame of reference is. So what do we mean? Okay, so we have x goes to x plus hx, where hx is very close to x. There's a little h, a little increment away from the flat shapes, where x, y, z is flat. And this h is a deviation from the flat. Now that corresponds to a situation like this. Here's our flat space. It's just the x and y coordinate to start off with. To a new x and y coordinate. Now we're only looking at one point. Here's the point, or some little area here, and there's a little h, okay? I suppose I should be using differentials for this. No, I can stick with the coordinates. There is a way to justify that later on. Okay, so this little h defines a slight deviation from the flat. It's a distortion, if you like. Here is the most important thing as far as I'm concerned with regard to general relativity. We can always choose, I'll say this really strongly, a set of coordinates which are locally flat. In geometrical language, that is this. We can always choose a set of coordinates which locally are geodesic. Yeah? Sometimes there's Riemann normal coordinates, there's different kinds of ones. But we can choose a locally flat system in any space-time. And it's wonderful how this fits in. How does this fit in with the physics? Locally, we can choose a flat place. We can get rid of the h's. Set them to 0, always, okay? Set them to 0 and we come back to our original space-time. Now I'm going to write coordinates in a different way. But before I do that, let's see how this fits in. I say choose or transform. That means if we're on our globally curved surface, We choose a set of coordinates which are valid only in this region and approximate the flatness. Like if we are in this room here, we can have a Cartesian coordinate system set down which deviates only very slightly from the big curvature that we see on the large scale. The small scale curvature is almost negligible. Okay? What does that correspond to in physics? It's absolutely dead easy. Here's the Empire State Building. How we make it look like it. The Empire State Building has a crane, and there's an elevator. And there's another crane, another one. Okay, so this situation here corresponds to curvature being felt. The acceleration due to gravity here is 9.8 meters per second squared. This one here, what has happened? Now we can have our coordinates in this frame of reference, the coordinates of the whole building. This guy here now is in free fall. He feels light as a feather. He's floating around. He doesn't feel gravity inside here. We only see gravity observing him. That's the only effect of gravity that we see. We see him falling due to the force of gravity. But remember I said gravity is a fictitious force. The only force is the force holding the guy up, just like centrifugal force versus centripetal force. Exact same thing. This one is in free fall. The physicists won't agree with me out there when I say that, but it doesn't matter. It works. So, free fall corresponds to choosing a frame of reference which is locally flat. In other words, his frame of reference in the elevator is not curved. Yeah? He's in free fall. But it's only locally for him in his box. Outside, looking at the big picture, we can see the effect of gravity pulling him down. That's the curvature coming into play. But locally, in his frame of reference, by cutting the cord and going into free fall, he's chosen a frame of reference. Now, there are joy rides in amusement parks that actually do this. Give you a locally flat frame of reference when you jump and or bungee jumping, same thing, right? And you get to feel what it's like to be in an inertial frame versus a non-inertial frame. The only force, no gravity, is this thing here. That's a good place to stop, and we'll continue with, next time we'll continue with some of the technology of the topic. The Einstein summation convention, playing around with the metric. What's the metric? It's something that tells us how to get from one space time point to another. Geodesics, what are those things? All of those things come into play next time. So next time we have not exactly how to spell this, but we'll talk about the metrics, geodesics, summation convention, and Kronecker deltas. Maybe this guy as well. And how to use indices. IJKs, Romans, and Greeks. This will be for flat space, this will be for curved, or this will be for three-dimensional, maybe. We'll decide next time.